Sandbox models are a diverse and significant tool for the interpretation of geological processes. They provide cheap and concise data, allowing geological structures to be observed and controlled in a small-scale model. They provide a 3D and 2D perspective of processes that may not be completely visible in the field, and allow for the understanding of how sediments respond to compressional deformation. The hypothesis we are investigating is, does the deposition of sand during deformation alter fault propagation? We are investigating the deposition of sediment on an orogenic wedge and its impact on fault propagation. This relates to the Andes, where syn-orogenic sediment accumulated on top of the eastern cordillera of Bolivia as the Andean wedge was shortened and thickened. To compare a difference in the nature of faults from a syn-sedimentation orogenic wedge to an orogenic wedge with no syn-sedimentation, we are conducting an experiment with both a control sandbox and hypothesis sandbox, where sediment accumulation on the Andean wedge will be mimicked by sieving an additional cup of sand every 4 centimeters of shortening. The equipment required to carry out our experiments included a sandbox to simulate compressional stresses, a tape measure to record data at each 2 centimeters of shortening, a compass clinometer to attain dip readings, a 600 micrometer mesh sieve to ensure all sand used in the experiment had a similar grain size, a cup to maintain a constant volume, sand in a variety of colours, and a ruler to take measurements of the wedge. To better visualise the faults, coloured sand was alternated in approximately 0.25mm layers. To record both experiments, we used a phone on a stand. The wooden block represents compressional stress, the primary factor of the natural analogue that produces a thrust-fold belt. Wedge thickness and length are measured using a ruler and recorded into a table. Dip readings for the oldest faults, youngest faults, and the top surface are all collected by the compass clinometer. The same approach was followed in experiment 2, with an additional sieved cup of sand overlaying the wedge at every 4 centimeter increment of shortening to emulate syn-sedimentation. Both experiments exhibit a series of reverse faults, with experiment 1 also containing a back thrust, which forms due to movement on the hanging wall of the active thrust accommodating shortening. Faults forming first display shallower dips that gradually steepen over time as compression is applied and newer faults arise. Both experiments portray folding until a fault occurs, continuing to deform and fault as compression continues. Overall, the number of faults increased throughout both experiments. At maximum shortening, experiment 1 contained 8 faults, whilst experiment 2 only contained 5. The faults within experiment 2 are longer and larger, with a greater distance between them than the faults in experiment 1. Experiment 1 reaches much higher dip angles than experiment 2, suggesting more internal faulting occurred. This is true when looking at the sandbox cross-sections, with the control sandbox sustaining 8 faults, whilst the syn-sedimentation sandbox could only maintain 5. The youngest fault angles for both experiment 1 and experiment 2 do not differ much from one another, both following a fluctuating sequence, with the final measurement being a dip of 18 degrees. This suggests that increased deposition doesn't affect any new faults occurring during orogenesis. Experiment 1 generally follows a consistent pattern, where dip angles of the oldest faults gradually increase. 16 and 18 centimeters of shortening appear to be an exception, with dip angles decreasing and plateauing, but then returning to the original trend at 20 centimeters of shortening. In comparison, experiment 2 exhibits a fluctuating trend, with dip angles increasing and decreasing. This suggests the dip of the fault varies abruptly at certain intervals, particularly after the addition of sand. These fluctuations indicate that increased deposition alters the older fault angles during orogenesis. Fossman states the critical taper is the equilibrium angle of a wedge. As stress is heightened, deformation and faulting occur. The results seen in experiment 2 exhibit a fluctuation of wedge angles, providing a clear example of when critical taper fails and where the material returns to its equilibrium. The addition of sediment decreases the average critical taper value of 30 degrees, seen in the thrust faulting of experiment 1, providing the theory that the critical taper angle equilibrates with a higher material volume through the collapse of the wedge. In the syn-sedimentation sandbox, the number of faults were reduced, larger and longer, and not as closely spaced as the control sandbox. Strecker states that the eastern Cordillera of Bolivia has a greater spread of deposition to other areas of the Andes. This resulted in larger frost faults in contrast to areas with less deposition, which consequently have smaller structures. The outcomes of our experiment portray similar characteristics, with syn-sedimentation sandbox having larger and longer faults than the control sandbox. The results indefinitely show a change in fault propagation. The findings indicate that periodically adding sand alters fault propagation by reducing the number of faults that the wedge can sustain. To establish more reliable results, this experiment will need to be repeated. If we ran this experiment again, we would continuously sieve sand over a 2 cm compressional period. Sandbox modelling isn't fully representative of the natural analogue. Structural development of a wedge can generate excessive topography as there is no erosional processes or isostatic adjustment that is seen in the Andes.